Good afternoon, everyone. Sounds like audio is great. My Wi-Fi today is not being my friend, so I'm probably going to be off camera most of the time. Sorry, I know you enjoy seeing this, but we're going to go off camera today. Anyway, boiler fundamentals, great class. I know many of you have been waiting for it. Great overview, all in 1 hour. We will be filling up that whole entire time for the most part. We're going to try and leave a few minutes at the end for questions. If I don't get to your question during the presentation, that's why. We want to make sure we cover as much as possible, and we'll take all questions at the end. And if we need to, we will follow up on an individual basis. Q&A, we have two ways to do that. You can do that in the chat. You can also do that in the little thing that says Q&A with the two little speech bubbles above it. I'm looking at both, so feel free to use whichever you're most comfortable with. If you would like to raise your hand, you can do that. I'll probably chat you to find out if it's a question or if you're having some technical difficulties. Other than that, I'm Sunday Perez, Corporate Marketing Manager, if you haven't met me yet. And today our illustrious instructor is Paul Campbell, our Corporate Technical Trainer, and I'm going to hand it off to him.
Fantastic. All right. Thanks, Sunday. Welcome, everybody. Listen, we really appreciate you taking some time out of your busy schedule to join us. We're going to be covering some boiler fundamentals. And if it's okay with everybody, I'm going to do the same as Sunday and kind of turn my camera off. It's just a bright light on my laptop. And after a while, it looks like I'm staring at the sun. I will bring it back on. I'll bring it back on as we get to Q&As towards the end. But with that, let's get rolling. If I can get to the next screen, we're making progress. So we're talking about fundamentals. When it comes to boilers, a lot of that can be intimidating. In 2 weeks, we're going to be talking about basic heat transfer, and whether that's through a shell and tube, where we're taking cold water, running it through tubes, and heating it up with either boiler water or steam, and leaving warmer than it came in, or we're doing that with the plate and frame, where again, we come in cold and we transfer heat and we leave warm. That's basic heat transfer. And we're gonna get into a lot more detail in 2 weeks. But when you think of a boiler, it's really nothing more than a fancy heat exchanger. The only difference is, instead of using steam or hot water, we're burning natural gas typically. You might also be burning propane or #2 fuel oil, depending on your burner type. But typically it's natural gas. Sometimes it's all electric, all choices. But keep in mind, it's nothing more than a fancy heat exchanger. On the system side, we're bringing in cold water, we're circulating around our heat exchanger, which happens to contain 2,500 degree flue gas, and we're simply heating that water up. So it's coming in cold, it's leaving warm, and headed out to our system, where we're either running it through fan coils or VAVs or some maybe a heat exchanger for some type of process. But all we're doing is transferring heat in a boiler. Okay, so we put it in fancy jackets and packages. We put touch controls on it. There's a lot of advanced features here, but when you break it down to the basics, it's nothing more than a fancy heat exchanger, okay? So we'll get into efficiencies and turn downs and other things. Just remember, all we're doing is transferring heat. Since we've got a burner installed and we're running natural gas, it has potential to go boom, and we try to avoid that. So there's some safeties and other things that boiler manufacturers pay a lot of attention to. Now, when it comes to a boiler, we have different materials that we can use for our for transferring that heat. You know, old school might be a cast iron sectional. You might also have some copper fin as a viable option. More commonly, you're seeing a lot of stainless out in the marketplace. The one that's not shown, that I'll give you an example in a minute, and that's steel tube. That's another option for materials. They all have different properties. They all have different resistance to condensing or non-condensing operation, low pHs, if you will. We'll talk about all that as we go through here, okay? We don't do a lot of math with boilers, but there is an equation that might help us a little bit, and that's typically BTUs out of the boiler, okay, or into our system, however you want to look at this, is equal to 500 as a constant times gallons a minute times delta T. This comes into play if we're trying to figure out how much flow we need across our boiler. If we've got it at high fire, and we might be designing for a 40-degree delta T across our boiler. So coming in at 100, leaving at 140, we can use this equation to figure out, hey, we need roughly 48, 50 gallons a minute of flow across this boiler in order to transfer heat or at full fire at a 40-degree delta T, okay? We're seeing a lot of electric with decarbonization going on right now. And 1 kW is equal to about 3,400 BTUs an hour. If we apply that to our million BTU boiler, that's about 293 kW. That just means your meter's going to spin a lot if your boiler gets to high fire, okay, or full output on an electric boiler. Let's talk about some different categories on boilers. Old school might be an atmospheric boiler. And one way to think about that, that's kind of like the barbecue on your back deck. You typically control the burners simply by controlling how much fuel is leaving your propane tank. You do the same thing on a boiler. We control the fuel supply, but the air simply comes from the surrounding space. We generate hot flue gas, and either we're cooking burgers on our heat exchanger, or in this case, we actually flow water through it, and we're picking up heat and sending hot water out to our system. The rest of that hot flue gas carries over across our grill or our heat exchanger in this case, if it's a boiler, and we typically collect it in a vent or flue, and we get it safely out of our mechanical room or out of the building, okay? So really it's very similar to a barbecue. The only difference is we don't have nice smells coming off of it, and you have to get rid of the nasty, the toxic air that's coming off of our combustion down here. So very reliable, really easy to troubleshoot. If you've got a source for gas and you've got spark and water flow, you tend to have combustion and heat in your building. Now there's some downsides to atmospheric. One of them is efficiencies. They're not terribly efficient, typically 80 to 82% if everything's clean and they're straight from the factory. The other big downside here is the emissions. As far as what they're sending out into the environment, they tend to be pretty, I don't want to say it, not real friendly to our greenhouse gases. So they're putting out NOx levels of 200 to 400 parts per million. So you're seeing a lot of, I don't want to say it, air agencies, a lot of counties not allow atmospheric boilers anymore. First, because they're not efficient, and secondly, because they're not real clean or friendly to our environment. Okay. So what do we do to get around that? We put a fan on it. We put a fan on our boiler. So most boilers that you're going to see, majority that are out in the marketplace, all are, you can call them fan assist. They simply have a fan that allows us to control both the airflow and the gas flow, and improves our efficiency numbers. Okay, so we can be much friendlier to the environment if we're burning natural gas. So this is what a fan assist might look like. We're going to either pull combustion air in from the mechanical room, or it could be ducted from the outside and bring that into our fan, where it grabs the air and sends it into our, I don't want to say it, our combustion chamber, where this is with gas. We have spark down here, and we have heat transfer. Okay, so that's a good example of a horizontal boiler setup. You can also go vertical with the same configuration. Again, this is our air inlet. This is our vent, where flue products leave the boiler and head outside. Kind of looks like a big fridge, but just to save floor space. You can also look at some what we call forced draft. They're still a fan assist, but these are like power burners. Almost look like a jet engine, if you will. burning, again, natural propane or number 2 fuel oil like diesel. And all they're doing is they're sending hot flue gas down the center of the boiler. And this section is actually full of water. It's hollow in here, so you have water that circulates around and is picking up that heat. It all collects, and either you send steam out to the system or hot water, depending on how you have it configured, okay? You could take that same power burner and stick it into a steel tube design. So this is a good example of a bent tube or steel tube boiler. That hot flue gas is going right down the center, and then there's actually 5 passes before the flue gas leaves the boiler. So all different options for boilers. One thing I'm going to back up for just a minute. Forgive me for being off track. One term that will come up a lot is fire tube versus water tube. That's simply, how do I say it? A good definition of that is where's the fire going? Well, in this case, it's clear that we have water in the tubes and fire is outside of that. Industry move water to surround it. I'll give you an example of that in a few slides here. Okay, but there is a difference between fire tube and water tube. Simply, where's your fire? Is it in the tubes or is it outside of the tubes? In this case, it's outside. Let's talk about firing rates, and that'll run us into turn down here in just a minute. An old school boiler might be on or off. It's either going 100% or it's sitting there idle. You might have kind of a minimum turn down or a low high setup where the burner might be running at 50% or 100, or it's off. So not a lot of flexibility there. You might have a staged setup where you've got multiple gas trains and you can just bring them on as needed based on your load. Okay, not ideal, but it does allow you some flexibility. More commonly though, we're seeing a lot of boilers out there that are set up with a modulating design. Kind of like having a pump on a VFD, it allows that burner to modulate to track system load. So that's typically what we're seeing these days is a modulating burner. So just some quick examples. Stage firing, again, there might be 4 gas trains and you could bring these on as needed. It works very similar to your barbecue. If you need more heat, you're going to either crank it up or bring on another section of your burners. Okay, you're doing the same thing with this boiler. More common though, we're talking about modulation, and that allows your boiler or your burner to fire at a minimum firing rate and then increase as needed and operate anywhere in between. So very flexible, has a lot of advantages for tracking load and dealing with flexibility or changes in our system throughout the day. One thing you might ask is, how do we maintain good combustion as we modulate our burner or our blower up and down, okay, as we speed things up or slow them down? Now, I know this slide's a little fuzzy, so please forgive me. Don't focus on this too much. But what you'll see here is the manufacturer's got some fixed orifices, one for the air and one for the gas. It's typically 10-to-1 ratio between air and gas. So these orifices tend to be fixed to help maintain that ratio. And what you'll find is that a gas valve is set up as, we call it negative regulation, but basically it's along for the ride. It's reacting to the pressure difference on the air side. So if we're taking our boiler up to 100% fire, the blower ramps up, we bring in more air. As we're doing that, we get a higher differential across this orifice, and the gas valve says, oh, I need to open up and allow more gas to flow in. As we get close to set point and our boiler modulates down, okay, less air. As we slow our air down, this gas valve also goes closed or starts to modulate down because we have less pressure difference. So the gas valve's along for the ride as the blower modulates up or down. That's how we get good combustion throughout full modulation. So typically you check this at low fire and at high fire to make sure that combustion properties are right. And after that, the gas valve simply tracks, how do I say it, the burner modulation, okay? Hope that helps. Let me launch a first poll for you if you don't mind. Give this a shot. We're going to talk about turn down here. One thing to think about, at least in Portland, design day, or how do I say it, a worst case scenario might be 10 degrees. That might rise a little bit with global warming potential, but for a long time, it's always been 10 degrees. And we're going to design a boiler plant for that as our worst case scenario. But if you look at, we might spend 4 hours a year at 10 degrees, but majority of our time is really anywhere from 40 to 55 degrees. And again, I'm referencing Portland. So as weather warms up, we don't need full output from our boiler. We can actually deal with less heat in our building and still heat our classrooms or our offices. So this is typically what's happening. We spend a lot of time with warmer weather. As a result, we don't need our worst case scenario. I've lived in Portland all my life. I can't remember when we've gotten down to 10. Okay, so all this is saying is we're going to spend a lot of time not at 100% firing rate for our boilers. Let's talk about how Lochinvar handles some turn down differences, or how they handle staging within their boiler design. What they originally, when they first came out with this setup, they had 2 blowers, kind of a 1/3 or a small blower and a very large blower, and each one of these has a gas valve that goes along with it. They've got a 2-chamber burner design, so the small burner here handles loads from 5 to 20%. If 20% doesn't meet the hot water requirements for our building, then we open up the second gas valve, fire the second blower, and now we control from 20 to 100%, firing the whole burner. Okay, so it's kind of a 2-stage setup. More commonly, now what they've done is they've just gone with a single blower. They still have 2 gas valves, and they use something like almost like a butterfly valve. They call it an air damper, but the air damper stays closed for the first section of their burner, and then it opens to allow more airflow to fire the whole heat exchanger, okay, or the whole burner in this case. Now, if you have a nice sports car and it's a beautiful day like it is today, I think it's supposed to be 70, 76, 78 here in Portland, and you get it on the open highway, nobody's getting in your way. You're going to be a boiler at high fire. Okay, you are flying down the road. You're putting out as much as you can, or going as fast as you can, kind of like a boiler at high fire. The challenge is when you get into town or you get to a stoplight, your sports car are going to overheat. Okay, it's one way to look at turn down is when you're sitting at a light and you're sitting there at your engine's at idle. That's minimum firing rate for a boiler. That's same as minimum, how do I say it, idle on your car. Okay, so either 100% fire is a wide open road. Minimum fire is your car sitting at idle at a stoplight. So the question is, how low can you turn down your burner to keep your boiler online before you have to physically shut it down? So let me go ahead and end the poll real quick and we'll share results. Thank you everybody for taking a look at this. Let's see if I can pull that over here. What advantages are inherent with a high turn down boiler? Less cycling. That's absolutely true. High turn down means we're not going to slow our equipment as much, so that's an advantage. Longer lifespan on our blower and electrical components. Improved ability to track system diversity. Absolutely, this is a big one as well. There's a lot of changes in our system. I'll talk about that in just a minute. Annual maintenance required. Yeah, that's not really an advantage. uh, we'll get towards the end of the presentation, we'll talk about why maintenance is important. Better situated to handle fluctuations within gas pressure. This is kind of a loaded question, so forgive me. I wasn't trying to bait you on this, but most, how do I say it, most modulating boilers can deal with fluctuating gas pressure, but to maintain good combustion, we really want a fixed gas pressure into that boiler. So 7 to 8 inches is typical, okay? And then, sorry, no idea, that's okay. That's why we're trying to review turn down, and hopefully my little, I don't want to say it, my little example made some sense. If not, let's deal with that in the Q&A. Let's talk about some of the variables we have in our hydronic system. We've got some system pumps that are on drives, and they're going to speed up or slow down our system pumps as we have changes out here in the system. So these might be offices or classrooms that we have water flow going through. They're controlled with two-way valves. So as we leave our office or the classroom warms up because we have a lot of bodies in there, these valves are going to go closed, and our pump is going to slow down accordingly. You also have some minimum flow that comes around through our system, but all that is tracking through, in this case, 3 boilers. Now, each one of these boilers happens to have a motorized isolation valve. And we stage the boilers or control their firing rate based on leaving water temperature. So the more zones over here that are calling for hot water, the colder the water is that comes back to our boilers, the more that they have to fire to recover that heat or energy. So as we satisfy these zones, whether it's through a sun load or computers or lighting loads, as our system warms up, we obviously need less heat through our boilers. There's a lot of changes going on in our boiler plant for flow and temperatures that we have to react to. Okay, so a lot of flexibility in our system means our boilers also have to be very flexible. And we'll talk about that with staging and some other concerns. Let's jump into efficiencies real quick. This is always an interesting topic. We looked at our gas barbecue on our back deck, an atmospheric boiler. It's typically 80 to 82%. Another way to look at this, you're sending 20% of your energy right up the vent pipe. Okay, so not very friendly on the gas meter. If you're looking at a high efficient, these would be a non-condensing boiler, you're going to get those up to about 87, 88%, which still means you're sending about 12% of your energy right up the vent pipe. Okay, if you're looking at a condensing boiler, you're typically talking about efficiencies that are 90% or greater. Now, let's talk about, let me launch my next poll if I could. Thank you, Sunday, for getting those in. So all manufacturers have efficiency curves. I'm showing you a Lochinvar Crest, but again, all manufacturers offer their curves, and you'll notice they're all very similar. So what you're going to see here is a manufacturing statement that says, hey, this boiler is up to 99% efficient. The question is, how do you or product to be 99% efficient? Because that's a pretty good number. Well, if you look at this point, in order to get to be 99% efficient, we have to be at low fire, okay, or minimum fire in this case. And we also have to have 60 return water coming back to our boiler. So very cold water and minimum firing rate. Now remember at the start of this, we talked about a boiler is nothing more than a fancy heat exchanger. If we take this boiler and we drive it to high fire, okay, or 100% firing rate, you'll notice that our efficiency drops a little bit. It goes from 99% down to under 97%. And why is that? Why are we losing 2%? Simply because a lot of that heat isn't getting absorbed by our heat exchanger. We might lose lose some of that heat up the vent pipe, okay? We might lose some of it through our jacket losses, and we might also lose it through condensate lines. So our boiler's always more efficient at low fire versus high fire. That just, we have more surface area absorbing minimum heat than we do at high fire, okay? So you'll notice as we start to move out here, as our return water temperature increases, our efficiency gets worse. Now, let me go to the next little chart here, and then we might come back to this one real quick. ASHRAE has a nice little chart for us that talks about the dew point of natural gas. The dew point of natural gas occurs about 128 degrees, which means if we bring cold water back to our boiler, we're going to actually take some moisture out of the flue products. And if we do that, our boiler efficiencies improve, okay? If we have a non-condensing boiler, it means that the materials that are in that boiler can't handle the acid that would come out when we run natural gas below its dew point. So most non-condensing boilers, I would say all of them, are going to give you some type of minimum return water temperature that they want to see. So good example, copper fin, minimum return is 130 degrees. Cast iron sectional, minimum return is 140. Okay, some boilers are 150. They don't want you, how do I say it, taking moisture out of the flue products. Now, if we come back to this efficiency curve, a condensing boiler is obviously the most efficient here at very low return temperatures and minimum firing. Now, I think that's one of my poll questions. We'll get to that in just a minute. Now, the shame of this is if you put this boiler into an old school system, meaning a system that was designed at 180 degrees out and 160 back on return, you'll notice that this boiler is only going to run 87% efficient, not 99% that you thought you might get. Okay, so it's based solely on return water temperature and firing rate. More commonly, we're seeing engineers design a system for 140 out and 100 degree coming back. So instead of a 20 degree, a 40 degree delta T. And that 100 degree return gets us into the mid 90s on our boiler efficiency, trying to improve that efficiency number. Okay, let's talk about what's happening inside the boiler itself or a fancy heat exchanger. If you bring cold water back to a boiler, meaning less than 130 degrees, you're actually going to cool down the products of combustion, in this case your natural gas, below its dew point, and as a result you're going to get some moisture that comes out. Okay, and that moisture, again, it's on the flue product side, okay, or your gas side. It's going to collect down here into a collection pan and then get out of the boiler. We have to get it out of the boiler. Nothing happens on our system side. That's simply a closed loop system that's I don't want to say it, pipe that's enclosed with water. Nothing's going to change there. It's on the boiler side or our combustion side that we're going to get some moisture out. So most condensing boilers are going to have a detail that shows you maybe a trap and then a neutralizer and then to drain. Okay, that condensate that's coming out with low return temperatures is acidic. That's usually why they have a stainless steel collection pan here. Has a pH from 2 to 5, so it's pretty aggressive. So you want to deal with that properly. You want to make sure you have a good pitch to drain, proper elevation. You also want to make sure you have some type of neutralizer that allows you to take that acid and turn it back into a neutral solution before you dump it down the drain. If you're mixing it with other fluids, you might be okay, but safe. I'd rather be safe than sorry, and that is to make sure it's neutral before it goes down the drain. If you want to double check your neutralizer, you can put a pH strip over here and take a look at the output, see how acidic it is. Most neutralizers are designed to last a year under full condensing mode, so this is a maintenance item. Now, forgive me, I got a little vocal on you there. Let me end the poll and we'll share results. What are true statements regarding condensing boilers? You can condense in all boilers. That's a true statement. Not all boilers are designed to handle the acid that comes out as condensate. As a result, yeah, it might tear up some boilers, but yes, true statement, you can condense in all boilers. Not all boilers are designed to handle it, okay? Condensation occurs due to low combustion air temperatures. A bit of a trick question. It's really based on low return water temperatures. So not so much on the air side, it's more based on water side. Okay, that's going to affect our natural gas combustion process more than air temperatures. Typical pH range for condensate is 2 to 5 when measured at the boiler. That's a true statement. Condensate neutralizers are required for the boiler and the flue. Again, I would tell you they're required. It's certainly cheap insurance, so you don't tear up your floor drains, okay, or your elbows. Um, Condensing boilers are most efficient at high fire versus low turn down. Yeah, I don't think this is worded real well, and forgive me, that's on my end. They're most efficient at high fire. Condensing boilers are most efficient at low fire, okay? And then sorry, no idea. Hopefully this helps to address some of those. Again, thank you guys for taking part in the poll. Most boiler manufacturers are going to have two options for you. They're going to have their line separated between non-condensing boilers and condensing boilers. So non-condensing means there's going to be a minimum return temperature that you have to keep these at, okay? And in this case, these are all copper boilers. So I'm going to tell you minimum return right off the bat needs to be 130 degrees. And we'll talk about how you might protect these if your temperatures are lower than that. But you have options to go horizontal or vertical as it relates to your floor space. If you want to go condensing, that's certainly an option too. There are no minimum return temperatures. You've got a lot of feature-rich products here, a lot of advanced controls when you go to a condensing boiler. For me, just make sure that you're taking advantage of the efficiency, and you do that with low return temperatures. Let's talk about if you've got multiple boilers in your plant and they happen to be condensing, how would you stage those? Would you bring one boiler on at 100% and then bring boiler number 2 on until it got to 100%, then bring boiler 3 on and 4 and 5? That's what you might think, but since they're condensing boilers, it makes more sense, more efficiency sense to fire them all at low fire, okay? Might be a little counterintuitive, but when you're dealing with condensing boilers, remember they're most efficient at low firing rate. So in our case, we've got 5 boilers, potential for 15 million BTUs worth of heat, but all told, they're putting out 825 by running each boiler at minimum firing rate, or in this case, 6%. And the goal is to maximize efficiencies, and you do that at low fire, okay? So this all comes down to coordination, minimum flow rate through the boilers, and kind of control sequence. Boilers are smart enough to do this, whether you deal with building management system or you let the boiler do its own control. Typically, the boilers are smart enough to stage based on efficiency. So again, just remember, fancy heat exchanger, the less heat we put into it, the more efficient it becomes. Okay, if we're trying to compare various manufacturers, or in this case, boilers, one really good option is going to AHRI. They have directories for both residential and commercial products. You'll find a commercial boiler section in here, and you can pull up any boiler manufacturer. The product that you might be looking for. In this case, we're looking at 100,000, but you're going to see efficiencies being listed or rated. The trick is the combustion has to match the O&M requirements. We're seeing some manufacturers cheat that a little bit, lean things out to maximize their efficiency. HRI caught them with that. So now they're requiring that all manufacturers have efficiencies tested as it relates to their O&M or their combustion process. Okay, so it's a good way to compare multiple manufacturers as far as an efficiency you might get um, throughout the life, how do I say, annually, okay, as you're firing your boiler. Let's talk about how we might protect a non-condensing boiler. So if you've got a boiler that has a minimum return of 130 degrees, but you're bringing some colder water to it, how do you protect it? Well, this is one option. Now this works better as a water heater than it does as a boiler. So, but bear with me a second. If we're pulling out of a storage tank, we might have 90-degree water coming to this. I'm gonna call it a boiler, but in reality, it'd be a water heater. Okay, let's just 90-degree water. If it comes into our boiler and leaves warm, how are we gonna get this above 130? We can add some circuit setters, basically calibrated ball valves, and by choking down on our circuit setter B, we create some resistance and force that hot water back into our return, okay? So we're gonna choke circuit setter B until temperatures over here on our return get above 130. Basically, we're constantly bypassing some of our hot water back into the return with the goal of keeping this above condensing mode. So this works really good when your return water temperatures are constant, and you do that off of a domestic storage tank. So this would be more a water heater than a boiler. I'll get to that in just a second. If we're dealing with the typical building system, typical closed loop heating system, we tend to use motor self-contained three-way valves. Now, these have a wax-filled element, kind of like the radiator in your car, and they simply stroke based on return water temperatures. So in this case, if we're less than 130, we open up the bypass and we continue to send hot water back into the return. And forgive me, I reversed this on you. We continue to heat this up until it gets above 130. And we basically ignore the system. Once we get our return above 130, we start to send hot water out to the system. And once all our system heats up and gets above 130, then we close the bypass altogether. Okay, but there's going to be times when this modulates and allows a little bit of system water in and continues to bypass some hot water. But these are all cheap protection if you decide to go with a non-condensing boiler. I hope that all that makes sense. Now, what happens if we condense in a non-condensing boiler? You've got, in this case, you've got a copper fin boiler that was run for 4 years in a condensing mode, meaning low temperatures in the school district. And you can see all the acid etching that's occurring on the copper fin heat exchanger in this case. And after 4 years, they eventually ended up with a failure. We've seen them fail in 6 months, in 9 months. Typically, it's less than a year. So in this case, 4 years is actually pretty good service. The shame of it, there's really easy ways to protect it, and we just talked about those. Either circuit setters or a self-contained three-way valve. Okay. Commercially, we tend to operate with steam boilers that are less than 15 pounds and water boilers that are less than 160 pounds of max working pressure and output temperatures less than 250 degrees. If you're dealing with industrial, you're typically dealing with higher pressure steam and potentially higher pressure hot water. Okay, but commercial world, we tend to spend a lot of time in section 4. Not that means much to you. If you get out of section 4, you're probably going to have a dedicated operator in your mechanical room to keep an eye on that boiler every time it's firing or in operation. So let me launch my next poll. And we'll get going on this. There was a little bit of confusion on this last time, so I've added a few slides to this. We have a lot of engineers, contractors, and owners that confuse a boiler with a water heater. So I just want to clarify that real quick. A boiler is designed for a closed loop heating system, and it carries an ASME H stamp. Okay. There's also controls and safety devices that are rated for a boiler. A water heater carries a different stamping from ASME. It's called an HLW stamp, and the materials tend to be non-ferrous. Okay, anything that's heating domestic water, you're typically looking at some type of copper, bronze, stainless steel. Where on a regular boiler, you've got a lot of iron construction designed for a closed loop system that's chemically treated, and there's not a lot of corrosion occurring. Okay. Now, manufacturers offer the same product. They sell it one way as a condensing boiler, and they sell it another way as a condensing water heater. So this may not help things. Here we have a gray box set up as a boiler, carries an H stamp. You'll notice that we've got a heat exchanger here with a burner that radiates out. We've got water that flows through the tubes and picks up heat from the burner assembly. Okay, this is set up as a boiler. We go to a light gray box now. Same, you'll notice, same heat exchanger design, but this is set up as a water heater and carries a different stamping from ASME. You cannot use a water heater to heat a closed loop hydronic system. Okay. We see a lot of engineers, and I'm not picking on engineers, owners and contractors. We get a lot of calls when somebody sees a dedicated appliance heating a storage tank. They tend to call this a boiler. And we've seen engineers say, hey, if this thing gets over 400,000 BTUs an hour, we're going to call it a boiler, even if we're heating domestic water with it. My caution is this creates a lot of confusion. Not only if you install a boiler here and it needs to be a water heater, the inspector's not going to buy off on it. We might have a crane pick to remove it and replace it, and there might be a lot of shuffling going on in the field. Okay, to me, any appliance that is heating domestic water, in this case a domestic hot water storage tank, should be called a water heater. Now, you can take boilers and heat domestic water, but the only way to do that is by separating it. So typically you've got a heat exchanger or an indirect coil in your storage tank. Okay, so boilers are chemically treated. You can heat a storage tank, but you've got to separate it with the heat exchanger. Okay, you could heat your system. You could put domestic priority on this if the tank gets cold. There's ways to do this, but these are boilers, and these water heaters. Okay, not to beat a dead horse. Let me end my poll and we'll share results. What is the difference between a boiler and a water heater? Any appliance greater than 400 MBH is called a boiler, regardless of application. We've seen some people fall into this. It creates confusion in the construction chain. So just be careful with this. That might get us all into trouble. There is no difference. Same appliance plus safety requirements. Yeah, that's not a true statement. ASME requires H stamp for boiler and HLW stamp for water heater. Yeah, very true. Boilers are rated to 160 pounds. Water heaters are rated to 80. That's a bit of a trick question. You still have high pressure water heaters. This 80 pounds comes into play in the fact that we can't have more than 80 pounds of water pressure in a typical pressure zone. So that's controlled more with pressure reducing valves in our riser schematics. Okay, and sorry, no idea. I hope this wasn't a trick question. We've just seen some people get burned by it, ourselves including. So I thought it might be worth stressing for just a minute. Okay, let's talk about venting. You know, we get very excited when we're going to put new equipment in a mechanical room. We're going to save a lot of space. Our controls are going to be great. Everybody's really excited about efficiencies and cutting that utility bill. But we see a lot of guys who forget about the importance of how are we going to vent this thing? How are we going to get that flue gas out of our mechanical room? There's different vent categories. Your gas barbecue on your back deck, your atmospheric boiler was category 1. Typically uses galvanized flue products. Anything else tends to be a special vent material. Okay, condensing boilers over here, categories 2 and 4, they tend to require either some grades of plastic or stainless steel, as well as category 3, which is kind of a sidewall vent application, or maybe a force draft application. A good example of a boiler that's installed with a a vent issue. This is an 88%, 87, 88% efficient boiler, not designed to condense in the boiler, but takes enough moisture out of the products of combustion that it has potential to condense in the stack, okay, or the flue. Contractor originally installed this with galvanized vent or B-vent and ran a long radius elbow, not like it's installed, but long radius elbow straight up through the roof. Okay, it took about 3 months for that acid that was occurring in the condensing process to eat holes in the venting. Facility guys got a little nervous, so they called the contractor back in. He reads the O&M and says, "Oh, I can't use this vent material. I have to use a high grade of stainless steel." So he repiped it, at least redid the venting, added a boot tee here to allow all that moisture to get out of the system. Unfortunately, while it was condensing in the flue products, it was also being allowed to rush back into the boiler. This particular boiler has an epoxy lined heat exchanger. You can see that it has, and it doesn't do well with acid, you can see that it has failed in less than a year. Okay, so the question is this a bad boiler or a bad install? And we fight this a lot as a rep. There's a reason I'm not showing you the name on the front of the boiler, because it doesn't matter. This could be anybody's product, but this is what happens when you have a bad install. You fight and you struggle because nobody's going to remember this story. They're just going to look at the name on the front and say, never again. That was clearly a bad product. But yeah, a bad install in the venting can certainly damage things. We see a lot of contractors looking to go cheap on venting, which is fine. You can look at plastic vent material, but be careful of your max temperatures. PVC and CPVC are good to 149 and 194. Charlotte Pipe also has a really nice outletter that says, hey, if you use our products for boiler flue and it fails, don't call us. It is not our problem. So we're seeing a lot of people try to transition into Polypro, which is a tested and listed system, and it also carries a higher max temperature. When plastics get soft, it acts like spaghetti. Your 90s hold up fine, but the rest of your vent pipe gets pretty soft and saggy. Now you're blowing potentially live combustion into an open space, and that can be deadly. Let me show you, I'm hoping this works. I know I'm a little short for time, so forgive me. Oh, this is great. Let me show you a quick example. This is a good example of, this is in Seattle. We've got some rain caps here on our boiler flue. It's a cold morning. We've got products of combustion that are trying to get away from the building. Down low is where we're trying to draw in fresh air. So what's happening is the flue products are trying to get out of the building, but they're hitting resistance here on the rain caps, okay, the top of the caps, and we kind of have a cold air inversion that's forcing those flue products down towards the roof of the building. That's creating flue gas recirc. That creates a lot of challenges for us, and the boilers tend not to like that. One fix to that is to go with exit cones or nozzle cones, okay? These simply allow your products of combustion to get away from the building and keep your flue, your air intake clean, and eliminates callbacks. So we really like exit cones or nozzle cones in lieu of rain guards, simply because they let those products of combustion get away from the building, away from your mechanical room. That's a good thing. Talking about, I'm going to say this, talking about venting boilers. There's times when you don't have an easy way to get those products of combustion out of your mechanical room. And sometimes you have to use a mechanical draft system. This is simply a fan up here that's controlled by a VFD, and it reacts to the pressure in the stack. We deal with US Draft. They are excellent at designing systems. You can certainly have multiple boilers tied into a common stack in a mechanical draft system on the roof. But dealing with US Draft, they're like, hey, if you've got a choice to vent without a mechanical draft system, that's the way to go. But if you're struggling getting vent runs out of your mechanical room, more than happy to sell you a system. Just be careful, this can get a little pricey on you. Typically $8,000 to $15,000 is a good kind of a good budget for a mechanical draft system. So that's one thing to consider when you're replacing boilers. You may have to upgrade your, more than likely, you're going to have to upgrade your vent system as well. Okay, let me launch one of my last polls here. I think we're getting close to the end. And I know I'm close on time, so I need to, please forgive me. I'm just going to fast forward through a few things here, and then we'll open it up to questions. One thing we're seeing a lot these days is move to electric boilers. And one thing you'll see with electric, there's a lot of contactors, a lot of steps, but you will not see boiler flue or combustion air. So when you look around this boiler, you'll notice that there's no vent pipe. There's also no ducted combustion air because it's electric. You don't need that. The meter is going to spin like crazy when the boiler fires, but you do not need, you don't need to vent it. Another challenge we see a lot on how do I say it, natural gas fired or condensing product is we see a lot of retrofits. And we'll see guys that try to take wrong venting. In this case, it's a Lumagal venting, and they will try to vent their condensing boiler in that. You can't do this. Here's another example of that. They will also try to terminate here where their existing boiler was, I don't want to say it, their existing boiler was obviously atmospheric. Here's a good example of galvanized flue. They've replaced that with a condensing boiler, more efficient, smaller vent pipe, but they're terminating it here. You can't do this. You can use this as a chase, meaning your flue gas has to carry all the way through here in the stainless vent pipe to get out of the mechanical room. But if you terminate at this spot, now we have potential to tear up this galvanized flue and do some damage. So yeah, this is another red tag issue. I got this one 2 days ago. I thought it was classic. Remember, you get acid when you're dealing with the condensing boiler. This is not the chair of choice. Okay, you don't want to be here on your break. It's going to cause some major problems. So yeah, don't sit there. You're seeing a lot of architects too not give adequate room for mechanical venting or vent runs that might get the products of combustion out the top of the building. So we're seeing a lot of kind of, I don't want to say this, sidewall vent applications. In this case, it's below the sidewalk, and you can see the plume that the boilers give off during high fire. Okay, this has a lot of potential repercussions. It also makes these windows not real usable. There's challenges here. We'll also see guys who might try to sidewall vent in an Alaska application. This doesn't work too well in Fairbanks where it gets to -50, and that moisture from the boilers is just looking for somewhere cold to attach. Okay, the PTAC units aren't doing so well. You've got a nice climbing wall here as a hotel amenity. You've got some challenges. Typically in Alaska, all the boilers vent straight off the roof with exit cones with the goal of getting that moisture away from the building. If we're going to go with a condensing boiler, you have to make sure to maintain it. It's a high efficient appliance that also needs annual maintenance to make sure things are clean, make sure combustion is stable, make sure air filters are getting serviced. So what you're seeing here is where the water level or condensate level reached on the back of the burner wall, simply because it won't drain through a clogged or dirty heat exchanger. Another good example of that, here's how it looks after 5 years of service, and here's how it looks after it was cleaned, okay? Typically, you're into a boiler every 9 to 12 months for annual maintenance. So it should be something that you add to your list when you're considering a boiler choice. Now, unfortunately, American mindset is let's buy a new product, let's stick it in a closet, and we'll come back in 5 to 10 years and check on it. You can't get away with that these days if you're going high efficient. And the other thing we're seeing is kind of some big budget crunches, right? We don't have a lot of money left over for maintenance or service. So when somebody needs heat, they tend to grab the biggest C-clamp they can find so that they don't have to reset their manual reset high limit every morning, okay? Because all they want is heat in their school. What they forget is they've just kind of have taken out one of their safety devices. Now, why was this boiler tripping on a high limit? There could be a bird's nest in the flue. There could be too much electrical tape. It could be poor combustion. We don't know, but we know that by taking out one of their safety devices, they risk this thing turning into a bomb in their mechanical room. Okay, so yeah, there's safeties for a reason. If you decide to override it, you're taking some big chances. Now, I need to apologize because I feel like I've used the whole hour and that wasn't my intent. But listen, if there's any questions, we are here for you. I know I ran a little long, and for that, I need to apologize in advance. Sunday, forgive me. Are there any questions we should deal with?
We have 3 questions.
Excellent. Let's see what we can do.
First one, what's the design protocol to keep the return water temps lower?
Oh, yeah, really good question. Typically, you're designing your system for those low return temperatures. So like a VAV box that's got hot water coils in it, you might take those from a 2-row coil to a 4-row coil. That's hard to say this afternoon. But by adding more coils, you can get a higher temperature drop across those, which allows colder return temperatures back to your mechanical room or to your boiler to make it more efficient. But yeah, that's part of the system design. That's a really good question.
Okay. Let me get that one. Next question. You talked about the difference between a boiler and a water heater. Can you please also comment on what defines a steam generator?
Yeah, I guess I have to be careful with that. So there's steam boilers and a steam generator. We have a clean steam generator, and all that's doing is taking dirty steam from a steam boiler and running it through a coil to boil off RO or DI water to create clean steam. So you've got a boiler and a generator. So I'm not sure how to clarify that much better. Yeah, typically you're not. Sometimes you'll take hot water and run it through a coil to generate steam, but typically it's a dedicated boiler doing that. I know that's not a great answer. So if we need to clarify more, speak up or let us know.
Great. John, you can also follow up with one of us on email too if you want to discuss it further.
Yeah, certainly.
Okay. Can you talk a little bit about minimum flows for different types of boilers as well as minimum system volumes?
Oh boy, that's a loaded question, a really good question. And I don't know that I can talk too much about it other than it's something that we need to consider when we're laying out a system and selecting a boiler. So every boiler has minimum flow requirements to it. Some manufacturers will tell you they have no minimum flow requirements. But if you think about a boiler that's got a burner that's firing, you better have some water going across it. Otherwise, things are going to increase in temperature. So it's just a matter of time before it cycles off. If we want to talk about system volume, all that comes into water flow and the delta T we're designing out in the system. A lot of that comes into play if we're maybe more on the industrial than on the commercial side. But if you've got a process where you've got 10 tanks, but we potentially are only serving one, you might need some extra volume in there. So yeah, now you can get into a buffer tank or some other things to add volume to your system to keep your boiler online longer. But that comes down into firing rates as well as system design. Really good question. I'm not sure I'm answering it very well. But yeah, again, if you want to take it offline, happy to open that up to conversation.
Okay, that was John. So if you have a specific scenario that you want to run by us, please feel free to email us directly. Probably Paul is going to be your better bet at getting what you need, to be honest, but it's Paul Campbell at chchydro.com. And if there's anything specific that you want to discuss around your question, happy to help.
Yeah, absolutely.
Okay. I know we're a little after 3. We're going to keep rolling through these questions. We just have a couple more. Feel free to stay
Sure.
on if you need to hop off. We appreciate you joining us today. And we look forward to seeing you at our next class. But again, if you want to stay on and listen to the questions and responses, please feel free to stay on. Next question. Why are larger boilers rated in horsepower?
Oh, that's a good question. Yeah, really good question, actually. So when you get into a forced draft burner design, they tend to be in horsepower. And we can convert horsepower over into BTUs. If you ask me what that conversion is right now, I might be a little fuzzy on that. But yeah, there's a simple conversion to take horsepower and back over into BTUs. But anytime you're dealing with a forced draft, kind of a nozzle design or like an aircraft engine, a power burner, they tend to be in a horsepower. And yeah, it's just a matter of converting that into BTUs. You might call that a real boiler, right? Something that's over 6 million or a very large size. Yeah, they tend to be in horsepower. It's a good question. I don't know why there's a differentiator there. I just know that for that burner, they tend to be in horsepower versus BTUs.
Great.
But they're one and the same.
Awesome. Okay, for domestic water heater with higher return temps, is a condensing boiler less desirable? If I said that right.
Yeah, it's a good question. To me, you have to look at your efficiencies, and so if you're keeping a storage tank at 140 degrees, in reality you might get 90 to 100 coming out of it every time it goes to a water heater. But if you're keeping that storage tank at 160 to 180, then yeah, you might have temperatures that are warm enough where a condensing water heater does not make sense. If there's rebates from your utility, that might help offset that. So it really all comes down to kind of comfort level, maintenance requirements, existing equipment, as well as what your actual site conditions are. So yeah, do I encourage condensing boilers? There's some safety there, but they don't always make sense. So yeah, if you're running warm returns, you're not going to get a payback on a condensing boiler unless the utility is helping you with that, or you can justify it based on some cold starts in your system. But on the domestic side, that tends to be pretty stable as far as return temperatures go. Another good question.
Great. That was our last question. Got a few thank yous. Lots of thank yous. So we appreciate all of you joining us today. It's a great topic, and I know many of you have been waiting for this class to happen. So I'm glad those of you who attended made it. And we look forward to seeing you in our next class that will be coming out soon for registration. as well as your recording of this class. I had a few questions on that. So you will be receiving a recording via email from me in the next week. So thanks again. Have a great rest of your day, and we'll see you soon.
Yeah. Thank you, Sunday. Thanks, everybody.
Bye, everyone.